If we have this as our matrix for just a general differential equation like dx dt equals ax, we're typically going to expect our solutions to be of the form e to the eigenvalue t times an eigenvector. But this runs into problems if you only have one eigenvector or one dimension worth of eigenvectors, because we should expect two solutions since it's a 2x2 matrix. If we actually try finding the eigenvalues and eigenvectors here, though, how would you find the eigenvalues and eigenvectors of this? What's your usual setup for solving for the eigenvalues? Yeah, we take the determinant of a minus something I, let's call that lambda for the eigenvalues, and set that equal to 0. So we can solve for lambda by writing out that determinant. So that's just minus lambda to each of the main diagonal elements. Multiply that out, just multiplying across the diagonals and subtracting. Negative 1 times 1 will just be negative 1. So we get 3 minus 3 lambda minus 1 lambda, so minus 4 lambda total, plus lambda squared. Minus 1 is plus 1. So overall, lambda squared minus 4 lambda plus 4 equals 0. And how does that factor? Can you get a couple of numbers that multiply to positive 4 but add to negative 4?
2.
Yeah, 2 and 2, or negative 2 and negative 2. Lambda minus 2 times lambda minus 2 again. So that we got a multiplicity there, multiplicity here in the sense that this factor shows up twice in the factored form. So lambda equals 2, but that's the only factor. It's a factor that shows up, or it's the only root. It's a root that shows up twice. So you say lambda equals 2 with multiplicity 2, in the sense that it shows up twice in the factored form. And that means there's only one eigenvalue. This 2x2 matrix has only one eigenvalue. On its own, that's not necessarily a problem, because it's possible that that one repeated eigenvalue has two different eigenvectors. So in general, if that one repeated eigenvalue, if that one lambda has two independent eigenvectors, let's say v sub a and v sub b, then that's fine. We can just have e to the lambda t times va and e to the lambda t times vb. These would count as independent solutions, even though it's the same e to the lambda t, as long as va and vb are independent vectors pointing in different directions, then this is fine. These will still form a fundamental set of solutions. So we could do C1 times e to the lambda t times the first eigenvector plus C2 times e to the same lambda t times the other eigenvector. That still forms a general solution. The problem happens when that one eigenvalue only has one eigenvector, or rather one dimension of eigenvectors, because it has infinitely many eigenvectors. But in this case, I think they all end up being multiples of one single vector. So let's try that out. We know it is 2. Let me fill that in. And let's see if we can find the eigenvector. As usual, we'll start by writing out a minus lambda I augmented with the 0 vector. And now we know that lambda is 2, so we can fill in 2 for lambda. That means we're just subtracting 2 from everything on the main diagonal. 1 minus 2, 1 minus negative, or negative 1 as it is, 1 as it is, and 3 minus 2. When you row reduce that, what's going to happen? Yeah, second row is going to become all zeros. And we should expect that. We should expect one of the rows to cancel out because we are looking for infinitely many solutions. So add the first row to the second row, those cancel out. While we're at it, we could also multiply the first row by -1. So we just get 1, 1, 0. And then we rewrite that first row, the only remaining row, as an equation. And let's say our eigenvector is, I don't know, maybe QR. So our variables are Q and R. We got 1Q plus 1R equals 0. So Q has to equal -R. Substitute that in, replace Q with -R, and factor out R, and what's left? Yeah, -1, 1. And that's only one eigenvector. And of course, any multiple of it also works. But since there's only one free variable, this is a one-dimensional eigenspace. That is, the eigenvectors are just one independent vector and all its multiples, nothing else. We only have one direction worth of eigenvectors. And that's a problem. We've got our eigenvector, -1, 1. And any multiple of that also works. So if you'd like, you could also write that as 1, -1, or 100, -100, or -2 pi, +2 pi. The important thing is that the x and y coordinates are opposite of each other. It doesn't really matter what they are. But we now have our eigenvector. But there's only one of them. So the issue here is not only do we have a repeated eigenvalue, we also have a repeated eigenvector. So that's our x1. x2, though, we can't just have another copy of this. So what do we do instead? What was our usual approach back in chapter 3 if we had a repeated root for the characteristic quadratic? Like if you're solving a characteristic quadratic and you get r equals 2 and that's it, you've got e to the 2t as one solution. What would typically be your second solution? Yeah, multiply by t. So let's try that out and see if it works. We have dx dt equals ax. Now let's say we make the guess that x is t e to the lambda t times b. Then of course we're going to need its derivative. What would be the derivative of t e to the lambda t? Or how would we calculate that derivative? Yeah, we're going to have a, well, partly we're going to have a lambda brought out, but yeah, we're going to need the product rule. So we take the first thing exactly as is times the derivative of the second thing, which is lambda e to the lambda t. Plus, then we take the derivative of the first thing, which is just 1, times the second thing exactly as it is. So our derivative is going to look like this. Lambda t e to the lambda t plus e to the lambda t. And that whole thing is multiplied by b. So let me just distribute that out. Lambda t e to the lambda t, first part, times b, plus the second part, e to the lambda t times the eigenvector b. And then to check if this really works as a solution, we'll plug both of these back into the original differential equation and see if they're equal. So we write out dx dt, which is this whole thing we got so far. And we want to know, does that really equal A times our guess? And one thing we can do here, since t e to the lambda t is a scalar, we can rearrange this and get t e to the lambda t times AV. Since a scalar can be placed anywhere in that product. But what do we know about A times B if B is an eigenvector? From the definition of eigenvector, if a B is an eigenvector, then A times B must equal what? AV equals not zero. That would be if V is in the null space of A. But the definition of an eigenvector is that for purposes of these vectors, or for purposes of this vector, the matrix acts like just a scalar. This definition is the foundation of everything there is to know about eigenvectors and eigenvalues. Then an eigenvector is a vector such that when you multiply this matrix times this vector, the matrix acts like just a scalar multiplier. You get a scalar multiple of the same vector. Which means if we've got matrix A times vector V, where V is an eigenvector, the matrix can be rewritten as just the eigenvalue lambda. In other words, the matrix times the vector is the same as this scalar times the vector. So the entire right side of the equation just becomes lambda times t e to the lambda t times v. So we end up with, on the left side, from the derivative, we've got lambda t e to the lambda t times v, plus an extra e to the lambda t times v due to the product rule. On the right side, we've got matrix A times our guess, but because our guess is an eigenvector, that means matrix A acts like just a scalar lambda. So now that we've simplified this, are these two sides of the equation equal? Do those look exactly the same? If we take a look at this one term at a time, on the left side, we've got a lambda t e to the lambda t v. On the right side, we've also got a lambda t e to the lambda t v. And order doesn't matter because these are scalar multipliers. So those terms match up. But the problem is we also have this extra e to the lambda t v term here. And we don't have that on the right side. So these are not actually equal to each other, which means t e to the lambda t v on its own is not enough. T e to the lambda t v as a guess for our second solution does make these terms match up, but the product rule gives us this extra e to the lambda t v term that doesn't cancel out, which means we're going to need one more term in our guess to make that work out. And the way you can do that, the t e to the lambda t terms match up, but we've got an extra e to the lambda t term without a times t. So that means our guess is also going to need a plus e to the lambda t times something, so that we get an e to the lambda t times something over here that will balance this out. And this is going to be e to the lambda, same e to the lambda t, because it's still same e to the lambda t in our result. We don't want to change the e to the lambda t. but we're going to need a second vector here. Let me call that vector W for now. So we'll make our guess t e to the lambda t times the eigenvector we already have, plus e to the lambda t times some mysterious other vector that I'm going to call W. And then when we carry that through with the derivative, we get t e to the lambda tv becomes this same thing it had before. But then the derivative of e to the lambda t times W would be lambda e to the lambda t times W. So by modifying our guess with this extra term, we also get an extra term in the derivative. Any questions on that modified guess so far? So let's carry that modification into the check itself. This is going to modify both sides of the equation. We've got our lambda t e to the lambda tv plus e to the lambda tv as our dx dt, plus this extra term, plus lambda e to the lambda t w. And that better equal, I'm checking, so I'll put a question mark here, a times x, that's a times our entire guess. And we can distribute this. The a gets multiplied by both of these terms. A times t e to the lambda tv, plus also a times the new part of our guess, a e to the lambda t w. Any questions on that so far? And again, we can assume that a times v is the same as lambda times v. V is an eigenvector, so multiplying by a is equivalent to multiplying by lambda. So I'm just going to replace this a with a lambda because of the definition of eigenvectors. And now if we compare these, see if they're really equal. We've got lambda t e to the lambda tv on the left side, and also lambda t e to the lambda tv on the right side. Those balance out. And we also have this entire extra term from the product rule and our extra modified guess. But we now have this extra term on the right side as well. So as long as these are equal to each other, then our guess works. So that's our new requirement. We now require that a times e to the lambda t times w must equal e to the lambda t v plus lambda e to the lambda t w, where v is the eigenvector we already have, and w is this mysterious new vector. So these terms must be equal in order for our new guess to work. In other words, actually, if we said this equal to this, what factor shows up in every one of those terms? What's the one multiplier in all of those terms? In fact, in every term in this entire problem so far. Yeah, they've all got an e to the lambda t. So when I set these equal to each other, I'm going to go ahead and divide both sides by e to the lambda t. That way we can just ignore the e to the lambda t entirely. Dividing both sides by e to the lambda t, this is going to make the resulting equation much simpler. We now just have v plus lambda w must equal aw. And now we have an equation we can solve for w, because a is the original matrix, v is the eigenvector we already have, -1, 1. Lambda is the eigenvalue we already have, 2. And w is the only unknown left here. So we just need to solve this equation for w, and we'll have this new vector that we will use to finish off our second solution. Any questions on that so far? And how would you start solving this for w? How would you start isolating w in this equation? I'm seeing that part of the problem here is we've got W on both sides. Could we bring all the W's to one side? For instance, we could just subtract lambda W from both sides. Yeah, exactly. So we get AW minus lambda W equals V. And then since W shows up in both of these, we can factor that out. And of course, we can't just have A minus lambda, so we'll have to insert an extra times I in there. But we end up with A minus lambda I times W equals V. And notice that this is almost exactly like the equation we used to find the eigenvector in the first place. To find the eigenvector, you say A minus lambda I times V equal to 0. To find this new vector W, you said A minus lambda I times W equal to V, the eigenvector we already had. So this is very much like the process of finding the eigenvector, but it's sort of the next level beyond. And we call W the generalized eigenvector. In the sense that we are using essentially the same equation we would use to solve for the eigenvector, but we're taking it one step beyond that. Instead of A minus lambda I times a vector equals 0, we're saying A minus lambda I times another vector equals the eigenvector we already have. So that's really the requirement here. The requirement for this W vector is A minus lambda I times W equals V. Any questions on the process of finding that so far? So let's try actually calculating that. Now that we've got the one requirement that this actually needs to meet. Let me write that out. A minus lambda I times W equals the eigenvector we already have. So there's a very strong parallel here. Finding the eigenvector itself find the eigenvector, you set A minus lambda I times V equal to W. Or sorry, to 0. But then to find the generalized eigenvector W, you set A minus lambda I times this new vector W equal to V, the eigenvector we already have. So that's the general process we're going to use here. And of course, now that we've got that, you don't have to go through that entire derivation process every time. We can just say, as soon as you know you have a repeated eigenvector, if you have not enough eigenvectors, you can assume that the other solution is exactly this format, T e to the lambda t times the eigenvector you already have, plus e to the same lambda t times this new vector found using this process. Any questions on the theory behind that so far? Then let's try actually calculating this. If we set up A minus lambda I as before, so A minus lambda I, but instead of augmenting that with the 0 vector, we're going to augment it with the eigenvector we already have. So let's try that. A minus lambda I would be this, but with 2 subtracted from the main diagonal. So 1 minus 2, negative 1 exactly as it is, 1 exactly as it is, 3 minus 2, augmented with the eigenvector we already have, negative 1, 1. And then if we try row reducing this, what's going to happen? Yeah, we still get a row becoming 0. Same process, we add a row 2 to row 1, 1 plus -1, 1 plus -1, 1 plus -1. Those all become 0. And while we're at it, let's also multiply the top row by -1. So we end up with 1, 1, 1. And then the second row is all 0, so I'm not even going to bother writing it out. And at this point, if we now write out our equation for the resulting vector, let's say we again call these Q and R. Then we get, instead of Q plus R equals 0, we get Q plus R equals 1. So if we solve for one of these vectors in terms of the, or one of these values in terms of the other, instead of getting Q equals -R, we get Q equals 1 minus R. So if we write out our vector W, we think of this as QR. We now know Q can be rewritten as 1 minus R. So 1 minus R, R. And if we split this up based on constants versus variables, we could write this as a constant vector plus a variable vector. So 1 minus R, I'm going to split that into 1 plus -R. R could be just thought of as 0 plus R. Now we've got a constant vector plus a variable vector. And if we factor R out of the variable vector, what's left? Yeah, factor out R, we're left with -1, 1 times R. And where have we already seen -1, 1? Yeah, that is the eigenvector we already have. In fact, this is going to be, in general, what happens here. When you solve for W, you're going to get some constant vector plus any multiple of the eigenvector you already got. And we can actually ignore this -1, 1. First of all, because R could be any scalar, including 0. We could just set R equal to 0 and this drops out. But also because when we plug this back into our guess, e to the lambda t times W, e to the lambda t times 1, 0 is genuinely new information. But e to the lambda t times -1, 1, we already have that. That's part of our x1 solution already. So we don't actually need to consider the -1, 1 part. The generalized eigenvector is technically anything of this format, but we only need one example. So we can ignore the R times -1, 1, just set R equal to 0, and focus on this as the W. This is the generalized eigenvector. So that's W. We now have a value for that. Any questions on that so far? So let's fill that in. We now know W is 1, 0. Lambda is still 2. And V is our original eigenvector. -1, 1. So we now have our second solution. This is x2. T e to the 2t times -1, 1, the eigenvector we already have, plus e to the 2t times this generalized eigenvector 1, 0. Any questions on that so far? So let's try writing out our general solution then. We should expect the general solution to just be linear combinations of the two solutions we found. So some constant times x1 plus some other constant times x2, which is this whole thing. So this is one way of writing out our general solution. This represents all possible solutions of the original differential equation. Any questions on that general solution? And overall, this format should work anytime you've got a repeated eigenvector situation. If you've got only one eigenvalue and only one eigenvector and you expect more, then your first solution is e to the lambda t times the eigenvector. Your second solution is e to the lambda t times the same eigenvector plus this other part, e to the lambda t times w, the generalized eigenvector, which again you would find by setting a minus lambda I times w equal to the eigenvector you already have. Any other questions on that so far? So let's see if we can turn this general solution into a fundamental matrix. Because ideally, we'd like to be able to just write out some matrix function, some matrix whose entries are all functions of t, that we can multiply by the initial conditions to immediately get the specific solution, instead of having to solve for C1 and C2 individually. So let's try putting that together. And I think it's going to be useful here to actually multiply out everything except for the constants. So we could, for instance, write this as C1 times, bundle this e to the 2t into these. So negative e to the 2t, positive e to the 2t. That way we've just got C1 times a vector function plus C2 times, and then if we combine all this together, we've got t e to the 2t times negative 1 plus e to the 2t times 1 for the top coordinate. And then for the bottom coordinate, we've got t e to the 2t times 1 plus e to the 2t times 0. So this vector is just everything in the parentheses here combined together into one vector. We now have a linear combination, C1 times this vector function plus C2 times this vector function. And this is a very convenient way to write it if we're going to be doing anything with trying to solve for C1 and C2. For instance, we can now plug in, like, let's say we have the initial conditions. Let's say we know that x of 0 equals, I don't know, 5, 3. You could plug in 0 for t, simplify all of these, because all of the e to the whatevers become 1. And then you could set that equal to 5, 3 and solve for C1 and C2. But we can also set up a fundamental matrix here. And we can do that by writing this as a matrix times a constant vector. Specifically, if we just got a linear combination of vectors, we can always write that as those coefficients as entries in this vector, and these original vectors as columns of this matrix. So this first column can be this vector, negative e to the 2t, e to the 2t. Second column would be this entire vector. So probably want some more room here. Negative t e to the 2t plus e to the 2t, and then t e to the 2t. That whole thing times C1, C2. The reason this works is when we multiply this out, when we combine row and column, we're really just multiplying something from the first column times C1 plus something from the second column times C2. So overall, C1 gets multiplied by the entire first column, just like what we have here. And C2 gets multiplied by everything from the second column, just like what we have here. So this is a very useful way of combining a linear combination into just a matrix times a vector of coefficients. And this matrix technically counts as a fundamental matrix. But the problem is it's not a very useful fundamental matrix. It's not as useful because if you plug in 0, this doesn't turn into the identity matrix. Ideally, we want a fundamental matrix that turns into the identity matrix when you plug in 0. We want a fundamental matrix, and I think this is usually called capital Phi, such that when you plug in 0 for t, you get the identity matrix. Because that way, we could just multiply that whole thing times the initial conditions. If we know that phi of 0 equals the identity matrix, then we can just say phi of 0 times this C1, C2 vector equals the initial conditions. Because to find the C1 and C2, you'd be plugging in 0 for t anyway. So you'd have this matrix when t is 0 times C1, C2 equals the initial conditions. But if this is the identity matrix, if this value is the identity matrix, then you just get the identity matrix times C1, C2 is the initial conditions. Anything times the identity matrix is itself. So that means C1, C2 is just the initial conditions. So if we can rewrite this such that this becomes the identity matrix when you plug in 0 for t, then all you need to do is multiply that matrix times the initial conditions, and you'll immediately have the actual solution. Any questions on that so far? So let's try this out. For now, I'm going to call this the fundamental matrix that we have so far. I'm going to call that capital phi. This is just the notation used in the voice Defino textbook. So capital phi of t. Retweet it, looks kind of like a pitchfork. But the problem is when you plug in 0 for t, this does not become the identity matrix. We would like it to become the identity matrix. And this is related to the idea that if you have the function e to the something t, you plug in 0, you get 1 as a result. We want a function where a matrix function where when you plug in 0, you get the matrix equivalent of the number 1, so that it acts like e to the something t. So let's try that out. We have our psi of t, the fundamental matrix that works but is not yet good enough. And the problem with this is that it does not become the identity matrix when we plug in 0. Let's verify that though. Let's actually try evaluating psi of 0. If you plug in 0 for all the t values, what does this actually turn into? What numbers do you get if you plug in 0 for t? Can we actually do that? Just plug in 0 for t, e to the 0 is just going to be, yeah. So we get -1. Then t is 0, so this drops out. We just get e to the 0, which is 1. E to the 0 is 1 again. And then 0 times e to the 0 is 0. And note that this is very much not the identity matrix. But if something's not the identity matrix, you can always turn it into the identity matrix by multiplying by what? Yeah, you multiply by the inverse. So let's find the inverse of phi of 0. Phi of 0 inverse. And since this is a 2x2 matrix, we can use the shortcut. 1 over the determinant. So inverse of A, B, C, D is 1 over the determinant times dA, and then -b, -c. Just swap the numbers on the main diagonal, take the opposite of the other numbers. So 1 over determinant 0 minus 1. Swap these numbers. Take the opposite of these numbers. And then there's times -1 turns it into 0, 1, 1, 1. So that's the inverse of psi of 0. And now here's the really clever thing. We want a matrix function that turns into the identity matrix when we plug in 0. We want a matrix function, and I'm going to call this phi of t. And this is called the fundamental matrix. Not just a fundamental matrix, because there are many a fundamental matrix. But we want the fundamental matrix such that when you plug in 0, you get the identity matrix. And we can accomplish this by taking the a fundamental matrix that we already have, psi of t, and multiplying by specifically psi of 0 inverse. To create the fundamental matrix. Capital phi of t, the fundamental matrix, can be written as psi of t, a fundamental matrix we've already found as a function, multiplied by the constant psi of 0 inverse. That way we get a new matrix that is a matrix function, but when t is 0, we get psi of 0 times psi of 0 inverse. So the fundamental matrix evaluated at time 0 becomes psi of 0 times this constant psi of 0 inverse. And those cancel out to become the identity matrix. So that's what we're going to do. We're going to take psi of t, the matrix function we've already found, and multiply by the constant psi of 0 inverse. So multiply this matrix function, including t as a variable, times this constant matrix psi of 0 inverse. The result will be a new matrix function that we're going to call phi of t, the fundamental matrix. And that has the important property that when you plug in 0 for t, the whole thing becomes the inverse, it becomes the identity matrix. So that is really the goal we're looking for here. Because what we can now do, once you actually multiply that out, so multiply this matrix function times 0, 1, 1, 1, the result is going to be this matrix capital phi of t. And the big deal about this is that now you can find the specific solution using the fundamental matrix. X of t is just going to equal the fundamental matrix times the initial conditions. So you can now, once you find the fundamental matrix, you can multiply it by any initial conditions, and the result will immediately be the specific solution for those initial conditions. So that's really the big advantage of the fundamental matrix approach. It's kind of counterintuitive. It takes a while to get used to. Usually I find the C1x1 plus C2x2 to be a much easier way of understanding what's going on and interpreting the graph and the end behavior and stuff. But the fundamental matrix approach has this huge advantage that you can just multiply it by any initial conditions and immediately get the specific solution without having to separately solve for C1 and C2. The C1 and C2 values are built into this approach. Any other questions on that process? All right, then I will see you next time.